Hello everyone, welcome back. In this tutorial we will model our major helix or the outer helix to the best of our abilities. So as you can see here, let me rearrange my tools. As you can see here, this is the major helix, this is the outer helix. It goes down and then I think it just goes all the way there. And remember, in our analysis we have 6 tubes, so 6 of these. So as you can see in here, we have one here already, one here, one here, one here, and so on. And at a certain moment, the first one will wrap back up, and it just continue until it ends somewhere here. All right, with that said, let's get back to our code or our script. This is where we left off in the previous video. We created all the I-beams that follows our main curve. And what we want to do is we're going to create the major helix. You can leave this on or off depending on what your shaded mode is set to. I set it to rendered, which in Rhino, at least in my Rhino 6, it ignores the visibility toggle of Grasshopper and just renders the geometry. The only way for this to disappear is actually to switch shading mode or just delete this and it would just go away. But for me, it can stay. All right. Now, normally what I would do, or what people would do, most of us would just use whatever we have here and then continue on building that script. In my experience, for a script this large, or for a big project like this, it could get messy. It could get up to a point where something breaks and you will have very difficult time finding where the problem is. So I tend to isolate major sections or major parts of the model or of the project wherever I can. So for example, if I want to rename this part, I can just create a scribble. Let's set this to majorly high and just call it let's just call it I-beam, for example, so that I know, like, hey, this part is only responsible, and then Control G to group it. This part is only responsible for I-beam, so I can just move it anywhere I want and just be done with that. Or if something's wrong with the I-beam, I know where to look at least. So with that said, we do need to copy some of these because we need them. The first one being obviously the main curve, because that's where we create our plane. So we can actually shift select a lot of these because we need them anyway. You don't need that 4 because that 4 is just to get the height of the beam. So we can just drag, hold down shift, or yes, hold down shift, and then we can create a copy of it. So we're just gonna keep working on this one. We actually do need this one also, and then that one goes here because these are the major circles. Now, I mentioned that we have 6 tubes, so you might even want to do this instead, and then use interpolate to create a curve. But that's not how they created in the real version, which is this one. The curvature is actually really let's say it goes through a lot of points before it reaches one quadrant, let's say. And with points, I mean these sections, or all these. You can see all these as divisions on the circles that we need to do. So let's get that started. You can actually count how many sections how many points it takes before it reaches back, basically. But I actually went there to Singapore and counted this myself, and I had the results here. I took this on the phone and I just quickly scrapped the number in while sitting somewhere in a cafe or something. So what you see here is basically saying The 17 here is meaning you have, let me move this here. What the 17 means is actually I counted starting from here, right? Let me just use the same color. Starting from here, I was counting how many of these do I pass before I reach that end, and that's 17, which translate to, if I start 1 here, it means this is one section, which translates to 16 sections. Or if you want to count the points, then it's 17 points, right? And for the 13 is actually for the minor helix, so we can use that later on. But so we have 17 points above this line, and whatever's underneath the line is, if I can drag a photo that shows that, perhaps this one? No. Maybe this one could tell a bit, actually. It's very hard to say which photo 10 give you all that info. But I think with this one you can sort of make out how many points there is that we have to draw. So if I clear the screen for a second, so this, for example, these are the major helix, the ones that like this one. So we have that point already counted. We came up with 17, remember? So we have 1 here, 1, 2, 3, 4. Can I zoom? I better not zoom in. I think that's, so I think with this, what I mean is 4 is the bottom one, is the bottom line. So the other side will have the same one, which is 4, 5, 6, 7. So I think we'll have this. So that translates to 24. Yeah. So what that means is we have 24 points before one of these major helices backs around where the origin point is. And I'm not sure if this is pure coincidence, but the other way where you can see this is here, for example. I'm not sure if I have the correct one. Let me see if I can find one that shows it. You see what I mean. Actually, the same picture. This one. Cool. Yeah, this one could work. They're actually the same, but I'm looking at this minor helix because, or I can actually grab one photo next to it and that shows this one. So remember that we counted 24 points, okay? And what we need on this one is, what we can also count is, we have 6 tubes. I'm not sure if this coincidence, by the way. Starting here, there's 1 point, there's 2 point, there's 3 point, 4, 5. So on the 5th point is where another helix will start to wrap around, meaning in between the section there are 1, 2, 3, 4. 1, 2, 3, 4. 4 sections where between each where another major helix will start, and the same actually goes for the minor helix. And this might be pure, like I said, pure coincidental, or it's pure by design. But if you multiply 6 by the number of tubes, you also get 24. So we can actually test that by just using those parameters that we have. I think we have number of helices. Do I have that here? I do have that here. And what we can do with basically what it is let's just do it here. And what I want to do here is I want to say distance between helices. Can I call it that? And that's 4. Meaning it takes 4 sections before it reaches another helix. So I can actually take that and I'll put that here, and then I can do a multiplication based on a number and that, and what that will return is 24, and I can say I want to divide the circle by 24, divide my curve by 24. I should have 24 points, which I do. Okay, good. And that's how we're going to do that. And one thing we need to watch out for is where do we see, so let's isolate a small branch. So let's isolate the first circle so we can talk about that a lot better. And if I do, let's just 0, simplify that so we can just select that. So these are the circles of the points of the circle, right? And if I were to do a point list, and this will help us immensely down the line. I'll do 1.1 for the size of the point list that we're going to see. So as you can see here, our 0 point is where it should be. It's basically where the seam is of this circle, right? Which for us is not helpful, because then we have to start somewhere at the top, and then we have to either shift the list down by 2 or do whatever magic we have to in order to get our points, either start from here, which will be very beneficial to us, or start from there. So we need one of these 2 points, or perhaps here even, that could work. So one of these we need to do, okay? One way I found you can do that is you can use the same tactic that we use here, actually, is by rotating it by a certain degree, 90 degrees. That is valid for this part. But you can also employ a different methods, and I'm going to show you that method right now. And that involves, okay, let me explain the logic first. We have a circle here. We have a seam that starts here. And what we want to do, we want to move the seam either in here or here. Or we also talked about here. This is the middle point of a circle. What we can do is we can say like, hey, I want you to draw a line straight down, and where you intersect, that's where I want the new starting point to be. So then it will be 0, 1, 2, 3, 4. Then it becomes a bit easier for us to predict if we have any changes of our circle. Let's say instead of 24 points we have 48, whatever, then our method will ensure 0 will always start from here instead of somewhere here that we don't know. We simply don't know. So let's put that into action. What we can do is, like I said, we can start drawing a circle from the center. You can do a center point from here, but what you can also do is take the origin of our plane, okay, and just say I want this to go negative by 10. I just need it to be longer than, oh wait, actually, you know what, I can use the diameter as a length, because the diameter will always be longer than the radius. That's I don't know in what world that is not the case, where the diameter is smaller than the radius. So we can actually use that number to make sure that this always is the same for the event that you increase. If you were to put this as 10 and you increase your radius of your circle to like 100, then this method will not work, because then the line will be too short to cross anything. And now what we want to do is want to find the intersection, okay, Intersection of curve, I think we can find it here. Intersection of multiple, not multiple curve. We have curve and curve of our lines corresponding to their own circles. Let me disable that. So we can see is you can see all of these lines will intersect exactly where we want them to. And the neat thing about this, okay, we have parameters for both our lines of where they're intersected. And since B is our circle, we can have a look at the parameter that we need in order to move the seam down to the bottom. And as I expected, they all are the same number because, well, they all intersect in the same way. So now we can do is we can say move the seam of our circle based on that parameter. We might have to flatten this. Yeah, we have to flatten this because the data structure means this as one tree and 101 elements. This came out as 101 tree with each one element. So we needed to flatten that in order to make it work. And now, if I use this one, plug into a new reformed circle, plug into here, what you will see, the 0 is now on the bottom. But now another problem arises. It starts the other way while our curve should be starting this way and not that way. This is a super easy fix. We just flip the curve. You flip that, you plug that back in, and there you have it. The curve is now flipped, and the ordering is exactly what we want them to be. And now we can continue on with our, can delete all these, so you don't need them. Now we can continue on. Let me see, what can we do? Okay, let me visualize it by drawing an interpolated line first. Interpolate line. So if you interpolate the points as is, they just create their own circles back, except it's now open. So what we can do, we have to flip the matrix, makes the column the rows and the rows the columns. And what you get is just straight lines, which is not what we want. So the easy fix for this is we need to rotate each circle, each point, each set of point by 1 every time it goes down the line, and then keep on rotating it. So let's say 0 will start here. And actually, let me zoom in a bit more. So to visualize, what we want is 0 to start here, 1, 2, and on the next circle, we don't want that 0 here, we want it here, and then 2, and then so on and so forth, so that you can create this nice twirl, and that will represent our main curve, our main helix. So this component we will need, but not now. We need to fix this first. One thing we can do is we can just say shift list and make sure wrapping is on so that it keeps on shifting it and not end. And what you get now is it just it shifted all the points by 1, which doesn't help us. What we want is we want to shift each of these, let me simplify this so I can see it easier. Each of these trees, these 101 trees, 1 by 1. And what we can do that is we can generate a series that represent our shiftings. So let's see, start from 0. Yeah, we want to shift by 1. And the number of elements we want them to shift, it happens to be 100. Actually, we do have to do +1 because we need 101 numbers to ship 101 trees. So let's do that. We can plug that one in here. We need to graph this, obviously, because to match the data trees. And now we have all the twirls. Pretty neat, except that we have 24 major helices. That's not what we want at all. So we need to remove a lot of these. A lot of these actually. Um, One way we can do that is we can remove it after this part. But what I like to do is I like to reduce the amount of data that goes through further in the early stages as I can. And in our case, we can actually remove a few sets of points from here before we continue on. Okay, so what we're gonna do is, let me see, maybe I can use this one instead. Let me simplify this. I like simplifying it to make the trees a bit more readable, but it doesn't really make that much of a difference, at least for now. So we have 24 sets of 24 trees, each with their own points, which is good. We can actually come in here and delete those sets. Okay, so we need to code that. Here's what we can do. Let's group this first, so we can treat each tree as single item. Makes it easier for us to remove it afterwards. Okay, let me do that first. We don't need to see this actually. So we have basically 24 objects here, and we want to remove how much we want to remove? 18 of them. What we can do is we can just say call, and then we're going to use call pattern. What call pattern allows us to do is to have a pattern that we can use to call it. And that works well for us because we want to remove let me visualize that again. This one? No, this one. And 0 actually. So for example, the one that I have selected, I want to keep, right? Actually, let's give it this way, and then we visualize it again using a point list. Probably should have kept the previous one. Doesn't matter. Here we are. So what we want to do with the calling is we want to keep this because that's the bottom. We know there's a from photographs we know there is a tube that comes from the bottom. We don't want that. There's no tubes here. We know there's one here. We want to keep that one. So from this pattern, what we can see is we want to skip. We want to keep every fourth elements, right? Or actually, if you count this as 0, 1, 2, 3, yeah. So we want to keep every fourth element, and that's what we're going to do with our calling pattern. Is every fourth we're going to delete them. So let me swap back to my mouse. And I can visualize this very quickly by just showing you this. What am I going to do? Let's see. I think 0, 0, 0, 1. 0 means false, 1 means true. So if we call that, what we get is we need to ungroup it because you cannot interpolate a group. You need to ungroup it, then we get our points back, and we can do our list or our interpolation line. So this looks a lot more. I see an error already, which is that we are missing one. So I think something here is actually wrong. What we can do, I think we need to do this instead. There we go. So this is what we need, but I think in the end it's actually a lot more simpler if we don't start 0 here. To be honest, we might want to start it there. Actually, the first. We'll see how it goes. Actually, that problem could arise, but Again, you can keep this as is. I don't think there's going to be a lot more changes to this. But what I tend to do is I want to make this not in manual input. So I want the computer to generate that itself based on whatever input is here. Because if these change, chances are that this is not going to be valid anymore, especially if you increase the number of division points that we used here more than 24, and this will not make sense at all. So what we're gonna do is we do know how that come from. This come from here, and those are based on these. So we have a 4 and a oh wait, maybe I can use the 4 since I have 4 items there. What gives me ones and 0 very nicely? A range actually. What does the range want? 0 to 1. Number of steps. What do we get? Not exactly zeros. Oh wait. Aha. If I were to apply expression saying I want you to round the values. See, then I get, except that I'm getting 5 items. Why? Oh. X minus 1. But why is that one 1? You know what? Let's floor everything. Floor means round everything downwards. Now this is giving me exactly what exactly? I actually want the reverse of this. There we go. Now that works, and we can plug that in. That's it. That one is now settled forever based on the distance between helices. So that's solved. So this is the results of what we have so far. You might notice something strange is that there are actually no major helix there in the air. So as you can see here, there is no major helix that goes from here or here. What that means for us is that we need to find a way to further process our points. I believe somewhere here should be enough to effectively remove that part up to here, remove that one here, and remove that one here. And then the other way also. Because I do know that the same goes for the other end of the bridge. Since I have been talking for quite a while, and the topic to tackle this actually involves some neat play with list series and reversals. So I think it's best to save that for the next video so we can start afresh and maybe dedicate the whole video for that, because I think that part can take a while to process and understand, and for me to explain it in such a way that it is understandable for you. So we'll end this video here, and in the next part we will pick it up there and finish the lines that we will be using for our major helices. So I hope you've learned a lot about what we've been using here, especially the logic behind the moving of the sea, and maybe groups, how helpful they can be, especially also these two, which I do use very often in order to assess what are the situation, what are my points, how they look like, how they're ordered, how should I be approaching those. So I'll see you in the next video, and have a good one.